Okay, so I'm in lookup BST starter.racket, and I'm starting here from the data definition for BST that we did in the last video. And I've done a little thing here. I took the picture that we used to make the example data, and I just pasted it in right here above the example data. This is one of the things that's really neat about the Dr.Racket programming environment, is it lets us stick images right there in the code. And that's really great. You can take a picture of something like this that you either drew, or maybe you drew it on a napkin and scanned it or something, and stick it right there in the code. And what I would tell you about this is that you should enjoy it, because it's not true in every programming environment. At any rate, there's the data definition, and here's the problem. We're supposed to complete the design of the lookup key function. This function is like the lookup function we did when we represented account information using a list. Here we're operating on a BST. And I've got the wish list entry all set up here. We just need to finish it. So let's see. The signature, we're going to consume a BST and a natural, and we're either going to produce a value corresponding to this key, or we're going to produce false if we can't find it. So signature, purpose, stub, the next thing to do is to do some examples. And this is a case where we're really going to take advantage of the examples that we defined above, because BSTs are kind of big things to write in the middle of check expects. So what I'm actually going to do is I'm just going to, for a second, go take this picture and bring it back down here, just temporarily, to remind me what some of the key trees are. So let's see, let's start with the base case test. Check expect, lookup key, and we'll look in BST0, which corresponds to the empty BST. BST0 is false. There it is right there. So we'll look in there, and I don't know, we'll look for 99. We can't find anything in there, so it doesn't really matter what we look for, but let's look for 99. And of course, we can't find it, so we produce false. Let's try the next simplest case. Let's look up the key. We'll look in BST1. That corresponds to this 1ABC node right here. Let's look in BST1 for 1. And we better find it. It's the root of the tree. And if we find it, we're going to produce A, B, C. So now we're failing in the empty tree and succeeding in the tree of size 1. Let's also fail in the tree of size 1. So let's say check expect lookup key BST1 99. And you can't find 99 in that tree, so that's going to produce false. But you know, that's just failing down the right branch, because when we look in 1 for 99, it won't be 1, so we'll go look down the right branch. I'd also like to fail down the left branch. Lookup key BST1, let's look for 0. And that's also going to be false. Notice what's happening here is, because this data structure is richer, we need to think about succeeding and failing down both self-reference cycles. Here I failed down the 2 cycles, let's succeed down them. Check expect lookup key, let's say BST10, that's the root. And let's look in 10 for 1, and that'll be ABC. And I can even put a comment here that kind of starts at 10 and it goes left and then left. And I don't know, let's do a couple more. Well, all of these will be in BST10 because that's a nice big tree to work with. Let's look in 10 for 4, and that should produce DCJ, and that goes first left and then right. And now let's look in 10 for 27, and 27 should produce WIT, that goes right and then left. And finally, let's look in 10 for 50, and that should produce DUG, and that goes right and then right. So I've kind of followed both branches a couple times. And I'm just going to sort of format this out a little bit better because it's, I don't know, just because it makes me happy. Okay, So that's a bunch of tests. I sort of generated them systematically by kind of looking at the tree and trying to make sure that I was going deep enough to that I was trying to fail and succeed fairly deep in the tree, or at least too deep anyways. So let's make sure those are well formed, and they are well formed because they run. Most of them fail. All of them fail probably because the stub is just producing the empty string. So let's go get the template. We're going to template this according to BST, of course. Except that we've also got this additional atomic parameter. So we'll say, and additional atomic parameter k. And so each place after the dots, we're going to add a k. Well, hang on. First, I'm going to rename this to lookup key. I'm going to add the extra parameter there, k. I'm going to rename the natural recursions. And I'm going to put a note about I need to pass a second parameter there. It might be k. And then after each set of dots, I'm going to put k. So I'll put k there. I'll put k there. And I'll wrap these dots up and put k there. So just as we saw with lists, we're seeing that templating now is more than just taking the template from the consumed type. We got to do a little bit more work, but now we've got a template to work with. So let's finish up. The amazing thing is we're almost done. So let's see, the false case, that corresponds to this first test. And our intuition just tells us if you try to find something in an empty tree, it doesn't matter what you're trying to find, you can't find it. So we're going to produce false here. Okay. So let's see, what happens here? This, in some sense, is all of these remaining cases. And there's a bunch of them, aren't there? There's kind of the case where you're at the thing you're looking for. This is the case where you're looking for one and you're at one. So that's one case. And then there's a case where you're not at the thing you're looking for. Here you're looking for 0, you're at 1. So you go left and then you fail. And here you go right and then you fail. And in some sense, all of these others will succeed at the end. So there's really 3 cases. There's the case where you find what you're looking for, the case where you go right, you eventually fail, and the case where you go left and eventually fail. So that's 3 cases. 3 cases calls for a con in my book. What I'm going to do is I'm going to pick up this whole little thing here and delete it for a second, but I've copied it into my kill ring. And I'm going to say cond, question, answer, question, answer, question, answer. Did I get the parentheses right on that? Let me try Command-I and see if it looks right. And it does. Now, I've copied a whole whack of template here. I'm probably not going to have to use all of it, but it's all there just in case I want it. So let's see, what's the question in the first case? Let's make the first case be the happy case. We found what we're looking for. Well, what's the question for whether we found what we're looking for? Well, that's pretty straightforward, actually. It's just, is k, the thing we're looking for, the same as the key of this node? If the key of this node is equal to k, we're done. What are we supposed to do? Well, we're just supposed to produce the value. So because I did all that template copying, I'm having to throw a lot of stuff out. But in the next 2 cases, that's going to end up being useful. So that's the first case. That's the case where we found what we're looking for. The next case is the case where we have to go left. Now, how do we know that we have to go left? Well, that's where the invariant comes to play. We have to go left if the thing we're looking for, the key we're looking for, is smaller than the key of the current node. So we'll put a less than here. And we're comparing to the key of the current node. And that's the question for, are we going to go left? Should we go left? Now, what does it mean to go left? Well, to go left is this natural recursion right here. That natural recursion. And most of the natural recursion is all teed up. The question is, what do we do for the second parameter to look up key? Well, the second parameter is the thing we're looking for, k. We don't need to change it at all. So this just becomes k itself. And then the other case is the other case. We could put an else here if we wanted to, because it's the only remaining case. But what you can also do is make the test more explicit, because this is the case where k is greater than the key of the current node. Should we go right? And if we're supposed to go right, well, this is going to correspond exactly to the case where we went left. There's the natural recursion we want. We just wanted pass k for the second argument in the natural recursion. Fix up my parens here. Put question marks here if we want. Let's try it. Oh, I forgot to comment out the stub. In 10, if we look for 4, we should get DCJ. Let's see, in 10. So this test failed. That means all the tests prior to it succeeded. So the LL success case passed, but the LR success case failed. So when I need to go right, that's here. Oh, here's the problem right here. I copied the wrong piece of template when I edited down. Oops, that's supposed to be an R. I bet that's it. All 8 tests pass. All 8 tests pass. Now, if you've been skeptical about basing templates on the template rules and our rules for forming type comments, here might be a good place to stop. This lookup key is actually a slightly complicated function, but it actually turned out to be quite easy for us to write it. And the reason it was easy for us to write it is that our rules for forming types are based on some solid theory in computer science. And our rules for forming the templates are based on some solid theory in computer science. And what that gets us is some templates that are guaranteed to traverse the entire structure accurately. And then we just have to control exactly what we want to do as we traverse that structure. And that makes it a lot easier to write functions like this that search structures like binary search trees. So as always, it would be a good idea to review this whole video. Before you do that, I want to ask you a question. I've got this con here in which there's no else case. If I bothered to put an else into it, then here's the question for you. Could this here ever get called? Could this ever need to run? And if the answer is yes, what would have to happen in order for it to run? This is a hard question. This is a hard question. What you might want to do is go rederive this whole lookup key first and think about how we got it. And then think about what might happen that would cause that ... to need to run. When would this else ever run? Have fun with that.